In our last video, we looked at differential equations that took the form a y double prime plus b y prime plus cy equals 0. Before that, we were looking at differential equations, we were looking at the form of the differential equation where instead of constants a, b, and c, the things in those positions could be functions. These could be functions of t, and we had a form for that. We said p of t y double prime plus q of t y prime plus, I don't remember what the other one was. Let's just say r of t y equals 0. But then we also said that we would prefer that we could write our second derivative term with a coefficient of 1. So we divided everything by the function p of t. And then we said let or define q over p, we're going to call that little p, and r over p, we're going to call that little q. So that let us write this as y double prime plus p of t y prime plus q of t y equals 0. Now this is the form that we're going to be working with in this section, but some of the things we want to talk about will apply to even more general differential equations. So for the moment, let's start with this, and let's say that even if this is not 0, even if this is some function g of t that's not 0, when you have a differential equation in this form, there's a uniqueness and existence theorem, an existence and uniqueness theorem that applies to differential equations in this form. And that says, if you have such an equation with initial values y naught and y prime naught. If you have those two initial conditions, and if p, q, and g are continuous functions, and they need to be continuous for the same reasons in the same way as they did when we were looking at the first order differential equations, the existence and uniqueness theorem for that, we're going to do this over an open interval I, that contains our t naught value, the value that we've plugged into the solution, right? Once we know what the solution is, or the general solution is, we can plug t naught in and we'll get y naught out, and we can plug it into the first derivative. We get the first derivative value out there. Contains the point, the value t naught, then this differential equation will have exactly one solution. It will have a solution, and that solution will be unique. So let's say that this equation has exactly one solution. And that solution exists, and the way your book says it this time is throughout the interval I. So if, for example, I have an interval that's going from alpha to beta, then some t naught value, it's an open interval, so say t naught is here, that solution will exist for the entire interval. And the entire interval, depending on the function, remember these functions have to be continuous, but depending on the function, that interval can be the entire real numbers, the entire real number line. So that means that alpha and beta can, in theory, go to negative infinity and positive infinity, either on one end or on the other end, or on both ends. Again, depending on the function. The first criteria is that p, q, and g have to be continuous on the interval. So if one of these is not continuous on the entire number line, then that restricts the interval over which we can make this claim. But the point of this, and I'm not going to belabor this anymore, the point of this is to say there is an existence and uniqueness theorem for this form of differential equation as well, for this form and for this order, second order. The other thing I want to address here is some notation that your textbook uses. Notice that if I have a solution to a differential equation, let's just write this out again. Let's say y double prime plus p of ty prime plus q of ty equals 0. I've reverted back to g of t being 0 here because this is, first of all, because that's what we're going to be working with in this section, but also because this is what this, I'm not sure how to describe it. It's a way of, it's called an operator. It's just a way of presenting the information. It's a little bit confusing. It's kind of like learning new vocabulary. As it turns out, it's really just a shorthand. It applies primarily to this second order homogeneous linear differential equations that we're going to be working with. So I've reverted back to that that notation, that the idea that g of t is equal to 0 rather than potentially some function of t that's something other than just 0. And I think the easiest way to describe it would be to say that another way to write y back from our algebra days is just f of x, right? That's our answer, as it were. It's actually f of t in this context. Doesn't really matter, but it's conventional in this environment in differential equations to use t, so we'll try to stick with that now going forward as much as possible wherever that's appropriate. And then the derivative of y, the first derivative of y, is just the first derivative of that function with respect to t, and the second derivative is just the second derivative with respect to t of the function that we are calling y. That function has a more formal name, f of t, right? And if you think about the fact that taking a derivative is doing something to the function y or doing something to the function f, then we're essentially operating on that function. So with that kind of in the back of our minds now, let's take a look at another way to write y double prime, etc. It's just f double prime of t plus p of t times f prime of t plus q of t times f of t. I'm intentionally leaving this space a little bit, this equation a little bit farther to the right than it seems like I need to, because I'm about to describe something that I will be saying this thing here. I'll write my equal sign. That this thing here that I'm about to describe is equal to this. And what this is a second order differential equation. But how have I obtained it, or how has it been obtained? I may not have obtained it. I may just have the differential equation and I have to try to solve it. But how has it been obtained? How has it come to be? Well, it's come to be by taking my function f of t and multiplying it. There's my function f of t, multiplying it by some other function. We happen to be calling it q of t at this point. Then taking the first derivative of f of t, see, I'm doing something to f of t. I'm operating on it. I'm taking its derivative. And I'm taking that derivative and multiplying it by a different function. It could be the same function, but it's likely to be a different function, so we give it a different name. And then taking the next derivative, taking the second derivative and using that here. So I've taken f, I've done a couple of things to it, and I've multiplied it by those results by some things. So I've been operating on it. And what your textbook does here is it calls this whole process L of f. It uses a different letter. It doesn't use f, it uses phi instead of f. But that's just a matter of choice of variable name, choice of function name, right? It's calling it phi to distinguish it from some other potential function f. But the point here is that when we use this notation, L of phi or L of f, or whatever notation we choose to use, what we're saying is this function, this operator here, takes this function f and does stuff to it. And what it does is, I'll come back up here, what L does to f is multiply it by q, multiply its derivative by p, take its second derivative, and add these things together in this particular way. So in a sense, we could write all of this by instead just writing this. And that's kind of the point of this notation. If I define L of f or L of phi, if I choose, or if you want to use a different function name, that's fine. If I define L of f as f double prime plus p times f prime plus q times f, then instead of writing this out each time, I can just write this out. So that's the purpose, at least at this point, that's the purpose of going to the trouble to write this thing out, to describe what this thing is. It's called it's called a differential operator. And you've actually met these before. We know, here's another differential operator. I'm writing that like a partial. That's not really what I mean. Okay. The operator here is this piece right here. Here's a function f, and what this operator is saying is take the derivative of, and what you end up with is the definition of that operator. So this is another differential operator. This is one you've seen before. We're really only saying that in this case, we have a very specific first and second derivative, sum of derivatives multiplied by other functions. So we're defining this operator in a very particular way. And I don't think it really actually gets used much beyond this, this section, except as a kind of shorthand. And I'm intrigued by the fact that your textbook, when it does use it, tends to use it in this complete form. It tends to use this whole statement, right, all together. So my main purpose in addressing it here is to help you see what it means, so that when you see it going forward, it's not some kind of foreign obstacle to learning the rest of what you need to know. The next thing I want to address sort of pretty quickly here is this thing on, it's called Theorem 3.2.2, which doesn't really need a number. It's called the principle of superposition. And what it says is if I have two solutions to a differential equation, y1 and y2, solutions to this differential equation, then this combination of y1 and y2 is also a solution. There's a y1 plus a y2, and they each have coefficients that can be different. They might be the same, but they can be different. And this is also a solution for whatever potential values of C1 and C2 are. Now, to figure out what C1 and C2 are, I would need initial conditions, and I don't necessarily have that here. But if I have two solutions, I can write that. I can write all the potential solutions as C1 y1 plus C2 y2. Y1 and y2 are known solutions, or they may not know them, but they are existing solutions. We have to assume that these two different solutions exist first. Once we know that they exist, we can combine them in this way. C1 and C2 could be 0, or one could be 0 and the other not. So just y1 is a solution. C1 is 1 and C2 is 0. If C1 is 0 and C2 is 1, then just y2 is a solution, and those two are represented there. But then these can be other scalars as well. These can be other multipliers as well. And this is just a nice compact way to write all the potential solutions. So I don't have to write every single one, right? So that's called the principle of superposition. And we've actually already discussed that. I did that in the preview, or the preliminaries video for the section before this one. And what's really neat about this is that I can add to it now that if I know some initial conditions, y of t naught equals y naught, and y prime of t naught equals y prime naught, or y naught prime, I guess. If in addition to the principle of superposition, I have those initial conditions, then it's always possible to find C1 and C2 so that y equals, I'll come back to this and address it again. That's why I'm trying to squeeze it in here. C1 y1 of t plus C2 y2 of t. It's always possible to find C1 and C2 so that y, this y right here, this is my answer, my solution, y equals, right? It's always possible to find C1 and C2 so that this solution satisfies our differential equation. And that differential equation is right here. Okay, now there's a condition on that, and we're going to come to that next. But I wanted to stick it in there because it does sort of, it's a nice extension of the principle of superposition. It's not actually part of the principles of superposition. I should probably put it in parentheses because it's an extension. And we're going to talk about that next. We're going to address this idea that if I have two solutions, I can write a solution in this way using this principle of superposition. And I know that that's also a solution, and that any combination like this is a solution. And the extension of that is that then I'm guaranteed to be able to find C1 and C2 as long as, and that's what we're going to talk about next. So I'll do that on the next screen. Okay, here's that statement again. Assume or suppose that we have two solutions to this differential equation, and also assume that we've been given two sets of initial conditions. The function y, the solution, evaluated at some t naught value, some value for t, gives us one answer, and the first derivative of the answer, evaluated at the same value for t, that same t naught, gives us another y value. If we have those three things, two solutions to this differential equation and two sets of initial conditions, then I can always find C1 and C2, these two constant here, so that this statement here, this equation here, this expression is also a solution to the differential equation given up here. And not only that, but it will also satisfy the initial conditions. So given two solutions to this equation and two sets of initial conditions, I can find these two constants so that this satisfies the equation and the initial conditions. If I put this dot, dot, dot right here, because there's a condition on this, I can always find those two equations, or sorry, those two constants, if I know some other piece of information, and that other piece of information is called the Wronskian. The Wronskian is a determinant. If you have taken linear algebra, then you know all about determinants. If you have taken calculus 3, you know something about determinants. And we're not going to dive into determinants in any kind of depth here because it's not really a part of this course. So I'm going to tell you how to find the Wronskian, and if I get a chance, I'll make a separate video that describes really what it is and why we use it. But for right now, I'm just going to tell you how to find it. Different instructors will have different approaches to doing this, and in fact, I was looking at Paul's online notes for this content, this part of this course, and I think of Paul. I don't know Paul personally, but I've looked at and used his notes quite a bit for various different things at various stages in my career, including as a student. And he's usually very thorough, but even he says in his notes for this particular concept, don't worry about where it comes from, just use our formula. So I'm going to describe to you what the Wronskian is. Before I do that, I'm going to describe to you what a determinant is. And a determinant is easy to calculate, especially if it's for a 2 by 2 matrix. If I have a matrix, let's call it M for matrix, and my matrix looks like this, where A, B, C, and D are real numbers. Let's do this. If that's true, then the determinant of M, which we write this way, means the determinant of M. we'd say the determinant of M, but most of the time we just write it like this. The determinant of M is simply equal to the product of these two values minus the product of these two values, B, C. And that's it. It gets more complicated if you have bigger matrices. Trust me, it gets way more complicated. But we only need this simple determinant of a 2 by 2 matrix, because the entries that we're going to have in our matrix, I suddenly feel like I'm talking about linear algebra, and I'm not. I'm simply using a concept from linear algebra that's going to help us do the work that we need to do in this context. So this is one of the reasons I put this on the other side of the screen. Another way to write the determinant of M, or the determinant of a matrix, is like this: A, B, C, D. So far it looks exactly like the matrix we had up here, but instead of writing these brackets around it, that represents the matrix. I'm going to write the same matrix, but just with bars. It kind of looks like an absolute value kind of thing. That's the exact same thing. What's missing is this little tiny piece of my bracket here, right? Instead of writing those brackets, I'm just drawing the vertical line. So that's another way to write it. But the result is the same. It's AD. I've just realized I wrote AB here. I meant AD, the product of the diagonal values, AD minus the product of the other diagonal values, BC. So very quickly, here's an example. If I have a matrix A defined by 1, -2, 3, 7, then the determinant of A, which I can write like this. It's not necessary to do it both ways. I'm just giving you both ways here so you can see sort of multiple representations. So when you see them later, you'll understand what's going on. That's going to be 1 times 7, which is 7, minus, get my other color pen here, -2 times 3. -2 times 3, which is 7 minus -6, or 7 plus 6, which is 13. So the determinant of this matrix right here is 13. It's a numerical value, okay? Now it's a numerical value because the values in my matrix are numerical. The values in, or the entries in my Wronskian, or the entries in my pre-Wronskian determinant, the determinant that I take, those are not going to be numerical. They're not going to be constants, but the principle is the same. So let me finish this statement here, and then I think what I'll do is try to condense some of this so it's a little bit tidier, and buy myself some space down here to finish my description over here. So I'm going to erase this and continue my statement so I can guarantee an ability to find these two values, so that this equation, this solution y, this particular combination of functions and constants, satisfies my differential equation and my initial conditions. But I can only do that if the Wronskian is not 0. Now the Wronskian is just a determinant, and I'll show you exactly what that is in just a minute. But my goal here is to take the Wronskian, figure out what its numerical or functional value is, and then evaluate that function. If it's a function, if it's a constant, then I'm done. But if it's a function, then I need to evaluate that function at my T0 value, which is the value I've been plugging in here, and figure out and just determine whether or not that's 0. If it's 0, all bets are off. I can't make this claim. But if it's not 0, if it's anything other than 0, then I have this guarantee. I can find C1 and C2. So how this is going to help us once we know how to find the Wronskian is, once I've got two solutions to my equation, y1 and y2, and I can take my initial values, I can compute the Wronskian. If it's 0, I'm going to stop, because C1 and C2 can only be guaranteed to be found so that this will satisfy the equation if the Wronskian is not 0. If the Wronskian is 0, then I can't guarantee a way to find these numbers. So that's the goal here. And so now what I promised I was going to erase some of the right-hand side here. I'll erase my example. I'm going to leave my definition of the determinant here, but scooch it up a little bit, I hope, so that it takes up less space. And then I'll use this bottom right-hand corner to do to show you how to find the Wronskian. And after that, we'll do an example. Okay, so my determinant definition was not sticking, so I'm just going to rewrite it here. AD minus BC. Notice that those components or those entries have to be in this order, right? If I have a matrix A that is A, C, D, B, then the determinant of A is going to be AB minus CD, right? So these, if A, B, C, and D are the same numbers here as they are here, but they're in a different order, I'm going to get a different answer for my determinant. That's important to keep in mind. I also have to, because of that, I also have to multiply these two first and then subtract the product of these two. If I take the product of these two first and then subtract the product of these two, I'll get the same numerical answer, but it'll be the opposite sign. And that's incorrect, right? There's a mathematical reason for this. It can all be explained. I'm not going to take the time to do it in this environment. But it is important to remember that this diagonal, the product, minus the product on this diagonal. Okay, now, what is the Wronskian? The Wronskian is a determinant. But what is it the determinant of? I'm using that form of determinant that I showed you at one point not too long ago, where instead of having brackets here, I have just the vertical lines. So it's an important distinction to make, because if you're writing a matrix, then it's understood that you're writing a collection of things in a particular order. Whereas if you're expressing the idea of determinant, you're expressing the idea of a numerical value, well, of an operator anyway, this product minus this product, right? So now we need to figure out what's going to go in those four places. And what goes in those four places is this. Your first solution, y1, evaluated at T naught. And I'm going to typically move this out of my way, not giving myself quite enough space. Your second solution, y2, evaluated at T naught. That's what goes in the top row. That's my A and my B. In the bottom row, I'm going to take y1's first derivative evaluated at T naught and y2's first derivative evaluated at T naught. That's what goes in positions C and D. So I have A, B, C, D, A, B, C, D. To figure out what the Wronskian is, I simply need to compute this determinant, and that is the product of these two things here. So I'll write that out first. I have y1 at T naught times y2 prime at T naught. And from that, I'm going to subtract the product of these two things, which is y2 at T naught times y1's determinant. Sorry, derivative. Did I say determinant back here as well? I meant derivative. y2's derivative, y1's derivative, evaluated at T naught. That's what the Wronskian is. That's all there is to it. Once we know what those solutions are, this looks messy, right? But once we know what y1 and y2 are, so we know what those solutions are, there we are, y1 and y2, and we know what our initial conditions are, we'll know what T naught is. We simply plug T naught into y1 and y2 to get these two numbers. I say numbers. They'll be numbers if you evaluate them here. You might choose to evaluate them later, which is why they can sometimes come out in the determinant looking like functions. But perhaps maybe we will just work with numbers here. So once we have those two functions and we know what our initial conditions are, we know what our T naught is, then for each of those two functions, we can take its first derivative and evaluate it at T naught. Well, actually, we don't need to, right? Because it's right here. We know if we plug t naught into y prime, it's going to give us this number right here. So that's what the Wronskian is. And why do we need it? We need it to guarantee that we can find C1 and C2. If we can't find the Wronskian, then there's no way to know whether we can find these two values. If we can determine the Wronskian, then there's a good chance that we'll be able to find these values. And what are the chances? Well, it's not so much chance as we will be able to find these values as long as this computation that we do over here returns something other than 0. Anything other than 0. If it's 0, we're in trouble. Well, we just can't progress, right? We're not going to find these numbers. As long as it's not 0, we'll know that we can find these two numbers so that we have a general solution. Once we've done that, I'll show you how to find those two numbers. But right now, let's just concentrate on whether or not it's possible to find those two numbers. So on the next screen, I know I'm doing a lot of different screens on this one, I'm going to do an example where I give you a differential equation. And for the sake of argument here, I will tell you what the two solutions are, and I will tell you what the initial conditions are, the two sets of initial conditions, and we'll use that information to compute the Wronskian and figure out whether or not we'll be able to find C1 and C2. So I'm going to do that on the next screen. Okay, I decided I did want to do a problem kind of right from the beginning. Instead of giving you the solutions, we're going to work out what those solutions are. I don't see any reason not to take advantage of the opportunity to practice, number one. But we do need to note that I've reverted back to constant coefficients here because we don't really have the tools we need to completely solve a second order differential equations if these are something other than constants. But I can still use the results we get from this to demonstrate the Wronskian and how it gets used. So let's see if we can remember how to do this. What we're really doing here is we're starting with the assumption that the solution is going to take this form, and therefore I know what y is, I know what y prime is, and I know what y double prime is. And so I can plug all of these things in, and I get r squared e to the rt plus 7r e to the rt plus 12 e to the rt equals 0. And I can factor out that e to the rt, leaving me with r squared plus 7r plus 12. Now, either this factor is 0 or this factor is 0 in order to get the product of the two to be 0. Well, this factor is never 0, so we can jump straight to r squared plus 7r plus 12 equals 0. We'll factor that. We get a 3 and a 4, a plus. Okay, so r equals negative 3 or r equals negative 4. But what is r? These are not the solutions to my equation. These are the values that I need to put in here. So the two solutions y1 and y2 are e to the negative 3t and e to the negative 4t. And of course I could have a constant in here. And we know that a general solution, based on the principle of superposition, we know that a general solution can take this form, e to the negative 3t plus c2 e to the negative 4t. So that's how we would go about finding a general solution. The question is, how do we find out what C1 and C2 are? Well, when these functions are just constants, we take our y and we can find our y prime. Y prime equals negative 3 C1 e to the negative 3t minus 4 C2 e to the negative 4t. We use this information to set up a system of equations, solve the system of equations, and you'll figure out what C1 and C2 are. But when we're dealing with functions, as we're going to be in a little while here, we can't do that. This won't it's not enough information, right? So we won't be able to get the values of C just from a simple system of equations that we can set up from here. So we need a different technique. The next thing we're going to do is we're going to use the Wronskian to determine whether these values even exist, right? Whether it's possible, shouldn't say whether they exist, whether it's possible to find out what they are. And the way we do that is to take our two solutions, y1 and y2, and use them to set up the Wronskian. Remember that the Wronskian is a derivative. So I'm going to have y1 here and y2 here, y1's first derivative here, y2's first derivative here, and then I'm going to take the determinant of that. Well, y1 is e to the negative 3t, and y2 is e to the negative 4t. y1's derivative is negative 3 e to the negative 3t, and the first derivative of y2 is negative 4 e to the negative 4t. And then I'm going to find the determinant of this. The matrix that I would have had if I'd set this up as a matrix, I would have brackets here, right? But I'm not just writing down a matrix. I'm saying this is the determinant, so I'm going to get rid of those. And that determinant is the product of these two entries in my matrix. So I'll have e to the negative 3t times negative 4 e to the negative 4t. And from that, I'm going to subtract the product of these two entries. So I'll have e to the negative 4t times negative 3 e to the negative 3t. And typically for me, I've run out of room. So simplifying, this gives me negative 4 times e to the negative 3t times e to the negative 4t, which is e to the negative 7t, adding my exponents, minus negative 3 times, so plus 3 times e to the negative 4t times e to the negative 3t is e to the negative 7t. And that is negative e to the negative, forgot my t there, e to the negative 7t. This is never 0. There are some Wronskians that when you work them out, they could be 0 at just the right place. We're not even really too worried about that because there are other places, there are other values of t for which there are solutions. It's only when the function, when the Wronskian is exactly 0, it's identically 0, it's always 0, like the function y equals 0, right? It's the constant function y equals 0. That's what we want to try to avoid. Here we don't even have that problem. E to any power is never 0, right? And the fact that it's negative doesn't bother us because instead of having a graph, for example, that goes like this, we have a graph that goes like, where's my pen? Goes like this, sort of. It goes like this. There we go. It's still never 0. So what that tells us is that I will be able to find the values of C1 and C2. I need to take, where's my general solution? Here. I'll be able to find the values of C1 and C2 in this equation, in this solution, by another method that we'll discuss here in a few minutes. It will be possible to do that. And that's what the Wronskian does for us. If you get to this point and you start running around looking for values of C and it turns out that you can't find them, or that it's particularly difficult to find them, or that there's no guarantee that you can find them, then you're wasting your time. The Wronskian will tell you whether or not it's worth pursuing that goal, right? In this case, we've determined that those two values are discoverable. We'll be able to figure out what they are. To do that, I'm going to erase some of what I've got here. I can erase this. To do that, we're going to set up another couple of determinants. C1 we can find by taking the value y naught, the value of the derivative of y naught, y2 evaluated at t, and the derivative of y2 evaluated at t. We're going to divide that by this determinant here, which in this case is negative e to the negative 7t. And C2, that should be a determinant, sorry. C2 is kind of the same thing, but sort of in a backwards fashion. I'm going to take y1's value at t naught first, and then y naught. and y naught's, sorry, y1's derivative at t naught and y naught's derivative. Take the determinant of that and divide it by, in this case, negative e to the negative 7t. All right, so what are those values? Well, y naught evaluated at t, at some t value, I'm going to need to know what that t value is. So I can't do this piece unless I have initial conditions, unless some initial conditions have been established. But for the sake of clarity in comparison to what your textbook has given us, we have here is a determinant divided by a determinant, and the top determinant is y naught, y2, y naught prime, y2 prime for C1. Notice that C1 uses y2 and C2 uses y1. And that just goes over y1, y2, y1 prime, y2 prime, and that's the same for both of these. So y1, y2, y1 prime, y2 prime. So we're actually, if we decide to go right through the process from beginning to end and try to discover what C1 and C2 are, we're going to need this determinant anyway, right? Remember that if we're working with real numbers here, real number coefficients, constant coefficients, then we don't necessarily need to do this because we can set up a system instead and find our constants that way. But if we have initial value, we would need initial values to do this part anyway. If we have initial values and we have non-constant functions here, then we don't, doing it using a system of equations, that's not going to work for us. What we need to do instead is set up this determinant, and then divide by the determinant we found. This is the Wronskian, right? I could say divide by W. Divide each of those by the Wronskian, which we've already computed, and not only will this part have told us that those two values can be found, but then we can use that information again and a couple of different determinants here to find out what those values actually are. So a little bit of vocabulary before we go on. I apologize for highlighting the wrong thing earlier. This is my general solution. And we're calling that the general solution. We've been calling it the general solution, and there's no harm in continuing. That's exactly what it is. But these two functions, these two solutions, now that I know what they are, and because I know the Wronskian of those two functions is not zero, in fact, it's never zero, I'm also going to call this set of two functions, this collection of two functions, y1 and y2, I'm going to call it a fundamental set of solutions. If you've taken linear algebra, you can liken this to finding a basis. But notice that both in that case, if you haven't taken linear algebra, don't worry about that. But notice that in the case of linear algebra, when I call something a basis, I'm calling it a basis, not the basis, because bases are not unique. The same is true here. Y1 and Y2 are two solutions, but because C1 and C2 could be anything, right? There are actually an infinite number of solutions here. In this case, C1 is 1 and C2 is 0. And in this case, C1 is 0 and C2 is 1. That's just one particular way of writing this general solution using specific values for C1 and C2. And here's another, but there are others, right? So this is a fundamental set of solutions. It's not the only potential one. But that's what we're going to call this collection of two solutions. They have to be, they have to produce a non-zero Wronskian. They have to be, again, using borrowing vocabulary from linear algebra, they have to be linearly independent. Okay, these two have to be linearly independent. And they are if and only if the Wronskian is non-zero. Now, it turns out that linear second-order homogeneous equations always have a fundamental set of solutions. Whether or not we'll be able to find them is another story, but we can say that, and I'm not going to try to prove that here, that's beyond what we need to do for this course, but we can say that having an equation in this form, remember these are functions of t, they're just constant functions, but even if they're non-constant functions of t, an equation in this form will always have a fundamental set of solutions. So that's kind of a nice thing to know. If you happen to be taking this class from me using the textbook that we use, then you'll find in example 6 on page 116, that the solution that we come up with for one of the solutions that we come up with, y sub 4 of t, includes a hyperbolic sine function. So I'm not going to address that because we don't always, depending on where you've come from, where you took calculus and how long ago, for example, from what instructor even, you may not even have met the hyperbolic trigonometric function. So I'm not going to address that example, and I'm not going to ask you to do any problems that will result in hyperbolic trigonometric functions. There are two other concepts addressed in this section in the textbook, and I'm going to address one of them here and the other one in the next section. For some reason, your textbook decides to address complex valued solutions very briefly in a theorem at the end of this section, even though it states right in the textbook, right next to that theorem, that we're not going to use that until the next section. So I'll come back to that theorem before we start the next section, but for now, I'm just going to ignore it. This is theorem 3.2.6 on page 117. I am, though, going to address Abel's theorem, which is theorem 3.2.7. In algebra, we learned that there are linear equations or quadratic equations, different degrees, different types of equations. Well, the same is true with differential equations. There are different classifications of differential equations. A differential equation can either be linear or nonlinear. It will have a certain degree, and it will either be what we call an ordinary differential equation or a partial differential equation. Your textbook talks about these in this order, whether it's ordinary or partial, then what about degree, and then whether it's linear or nonlinear. I'm going to do it in the opposite order just because I think it makes a little bit more sense. So what is a linear equation? Well, in algebra, it would be something like this. Y equals x plus 2, or even y equals the square root of 7x minus 3.8. It can be quite complex. What's critical is that the independent variable has a power of 1, right? When you graph either of these, you get a line, hence linear. A nonlinear algebraic equation might look something like this. Y equals 3x squared plus 2x minus 7, for example. So above the line, we have some linear equations, and below the line, we have a nonlinear equation because the independent variable is squared. We have 2 factors of x in this term. But there are other ways that you can have nonlinear equations. Here's another one. Y equals 3x squared plus xy plus y squared. Now, this equation still only has 2 variables in it, x and y, but there's no way to write this as an equation like this one, y equals on one side and nothing but the independent variable on the right-hand side. Here's another equation that looks like it might be nonlinear, but it turns out it's linear because I can subtract the xy from both sides, factor out the y, and then divide by 1 minus x. So I'm going to cheat here, I'm going to get y equals 3x over 1 minus x. Y is by itself on the left-hand side, and the only variable present on the right-hand side is x. So although this equation looks like it's linear, it looks like it's nonlinear because of this term here. It turns out it is linear. I just have to rewrite it first. I've actually rewritten that one up here in my list of linear equations. Down here I have nonlinear equations. Another way we can have a nonlinear equation is to have more than 2 variables involved. So for example, I might have z equals 3xy. Here we have an equation that has 2 independent variables and 1 dependent variable. If you've taken Calculus 3, you'll recognize this as the equation of a plane in 3 space or in R3. If you haven't taken Calculus 3, don't panic. Nonlinear differential equations are different in any case, but you do need to be able to identify them. So that's why we're taking the time to do this. Now, in algebra, these linear equations and these nonlinear equations are linear or nonlinear in terms of their independent variable. So this is a linear equation because when you graph it, it produces a line whose input values come from x, right? And the dependent variable is y. But a differential equation is linear or nonlinear based on whether the factor y is linear or nonlinear. So for example, I think I'll erase the algebraic equations I've got here because we don't really need those. I'm going to leave you at the end of this video with a screen that has examples of linear and nonlinear examples of differential equations of different degrees and examples of differential equations of the ordinary and partial types. So I'm going to erase the algebraic equations and we'll start a list of linear and nonlinear differential equations. Okay, this might be a good place to point out or to remind you that dy dt can also be written as y prime. And in a lot of cases, your textbook does that, I think primarily to save space. But it's good to be able to switch back and forth between those two different notations because you will see both. Okay, so what we have here is an example of a linear differential equation because you'll notice that the derivative that has been taken is a derivative of y in terms of x. This one happened to be in terms of x before I erased it. That's implied here because the x is the only other, besides the y prime, the x is the only other variable. But y prime dy dx tells us the derivative has been taken in terms of y, and when we look for y in the equation, not y prime, but y, we see that there is a y and it only has a power of 1. That is what makes this a linear differential equation, not the fact that the x is raised to the first power. In fact, if I change this to 3x to the fourth power, this is still a linear differential equation. It's not linear as an algebraic equation. It's not going to produce a line when you graph it, but it is linear as a differential equation. Now, I've made a note here that this has an exponent of 1, and I'm going to erase that because otherwise it looks like another y prime. So that is a linear differential equation. A very similar looking differential equation, instead of 3x to the fourth plus y, if we had 3x to the fourth times y, that is also a linear differential equation. Algebraically, we would have said, no, this is not linear because we have a combination of powers here that is not 1, but in this case 5. But because the y, which is essentially the thing that I'm looking for if I were to try to solve this equation, the y is raised to the first power, this is a linear differential equation. I can take second derivatives too. So if I happen to have an equation that looked like this, I would still call that a linear differential equation because y is raised to the first power. The thing that I'm going to be solving for is raised to the first power. It's pretty easy now to supply some examples of nonlinear differential equations. All I have to do is make sure that my y is raised to some power other than 1. 2 is an example. 1/2 is not 1, right? That's like times the square root of y. So that's not raised to the first power. So these are not linear, nonlinear differential equations. And in fact, regardless of the number of derivatives I've taken, if I have a function, I'll call that f sub 0 times y, well, we'll leave that one to the 1 power, plus a different function of x times y to the second power, and that can go on forever. We could have plus f, call it one f of 1, f sub n of x times y raised to in this case, that would be n plus 1, right? I suppose if I change these to match, then I wouldn't have to do that. I'll make this f sub 1 y to the power of 1, f sub 2 y to the power of 2, f sub n y to the power of n. Now, this is the function n being raised to the nth power. It's not the nth derivative, right? Remember that I'll just do this over here quickly. If we have dy dx, we write y prime. It's equivalent to y prime. If we want to take the second derivative, then we have the second derivative of y with respect to x, and we annotate it that way. The third derivative, we'll use 3 primes, and then after that, we start using a numerical, instead of tick marks or tally marks, we use numerical notation. But we have to put that in parentheses, and the reason for that is so that we don't confuse y to the power of n with y to the nth derivative, or the nth derivative of y, right? So that's a very important distinction to make. This is to the nth power. Even if I were to erase all these middle terms, the presence of y to any power other than 1, including non-integer powers, right, means that this is a nonlinear differential equation. Okay, so we've talked now about what it means to be a linear differential equation or a nonlinear differential equation. And in both cases, I have examples of linear and nonlinear differential equations that have been produced by taking more than one derivative, right? So what do we do with that? Well, it turns out I made a mistake when I was starting this screen for this. It's not called the degree, it's called the order. I'm going to change this. The degree would be the degree of a polynomial, say a x to the 5th type of polynomial. We would say that had degree 5. But the order of a differential equation is the number of derivatives that were taken in order to get that equation. So for example, my y prime equals 3x to the 4th plus y is a first order. My y double prime that equals 3x to the 4th times y is a second order. And my y triple prime, which is f sub 1 of x times y to the first power, plus f sub 2 of x times y to the second power, plus all up to f sub n of x times y to the nth power. That would be a third order differential equation. And that's all there is to that. We're going to be working with first order differential equations in the first third of this course, the first unit. We'll look at some second order differential equations in the second unit, and we'll take a look at what happens as you raise the order to, theoretically, to the nth derivative. We'll do that in the third unit. Now, whether or not a differential equation is ordinary or partial, an ordinary differential equation or a partial differential equation is determined by what kind of derivative you took in order to get it. All of the examples I've shown you so far are ordinary differential equations. This is, I'm going to use this one again, but I'm going to write it as dy dx equals 3x to the 4th plus y. That is an ordinary, first order, linear partial differential equation. What makes a differential equation partial is determined in part by, I'm not sure how to explain this. For many of you, well, all of you will have taken Calculus 2. Some of you will have taken Calculus 3, but some of you won't have. The prerequisite course for this class is just Calculus 2. And unless you've taken Calculus 3, you won't necessarily understand what I mean by a partial derivative. But if I have an equation, let's say a function z, I'll make a really easy one here, 2x squared plus y cubed. I can take the derivative of z with respect to x, and I get what you think I would get here, right? That's going to be 4x plus, but when I take the derivative of z with respect to x, then y is not something with, we treat this like a constant. Y is not an x thing, right? So we pretend that that's a constant, and we say that the derivative of that is 0. If I take the derivative of z with respect to y, I get, well, I'm taking with respect to y, so we pretend that this is constant, and we say that the derivative there is 0. And we get for the derivative of y cubed what you expect, which is 3y squared. And these are called partial derivatives, right? Notice that I use a subscript here and a subscript here. Another way to write this is, this second one anyway, is the partial derivative, it's a funky looking d, partial derivative of z with respect to y. It looks an awful lot like dz dy. It's kind of meant to look like dz dy, but it's also meant to look not quite like dz dy, so that you know that you're not taking the derivative of this thing called z only with respect to y, but with respect to y in light of the fact that there's an x in it, right? So this is just another way to write z sub y. This is the derivative of y of z with respect to y, so is this. So I would get the same answer here, 3y squared. And so you'll see different notations for this partial derivative stuff. These are, I'm going to erase this, I think, this stuff below the line here, and then I'll do a little tidying up. Okay, so here I've got my ordinary differential equation, or an example of one. It's just got normal d's in it, and I could write it that way, or I could write it as y prime, or I could write it as d sub x, which means take the derivative with respect to x, right? I could write it any of those 3 different ways. A partial derivative, using similar notation, I would write partial z partial x, or partial z partial y, depending on whether I was taking the derivative with respect to x or taking the derivative with respect to y. Or you might see z sub x or z sub y. A second derivative up here in the ordinary category might be something like, give myself a little bit of space here, d squared y over dx squared. That's the second derivative with respect to y. Sorry, the second derivative of y with respect to x. So we could write that, or we could write y double prime, or we might write dx x. That's the second derivative with respect to x. I'm not sure that that notation is actually quite accurate, but I think I'll punt and say it's okay. Now, in partial derivatives, our second derivative would look similar. Our notation would look similar here. We would have partial squared z over partial x squared, or partial squared z over partial y squared. Or we would have z xx or z yy. That means take the derivative of this. I've erased it now, of course. Take the derivative of a function that's got 2 variables in it, first with respect to x and then again with respect to x. Or first take it with respect to y and then again with respect to y. But you could also take that derivative with respect to x and then turn around and take the derivative again, but this time with respect to y, or the other way around. Okay, so those are all notations that you would see for partial derivatives when you just took the derivative once, or partial derivatives when you took the derivative twice. This class is not about partial derivatives, and it's not about partial differential equations. So we're not going to be working with any of these. But again, it's important that you understand when you see notation like this, that this is what you're up against. And so you won't be able to do anything with these ones, but recognize them when you see them so that you know that that's the case. Whereas these are all different ways to write ordinary differential equations. So you need to be familiar with that notation as well. So there are 3 different categories we're interested in here. Is the differential equation ordinary or partial? What is its order? And is it linear or nonlinear? We're going to be working with both linear and nonlinear equations in this class. Here, let me highlight a couple of things here. We'll only be working with ordinary differential equations, but we'll be able to do that with differential equations of any order. We'll first of the first order and then of the second order, and then we'll start to theorize a little bit about what would happen if it was even higher order. What would happen if it was any order? You know, if we don't know what n is, or we don't specify that n has to be a particular number. So, but that's actually in the third unit of the class. That's pretty much it for this video. I think I've covered everything that I wanted to say. In your textbook, there is a considerable, lengthy, really quite interesting historical note. If you're using the paper version of the textbook, it's on in the 11th edition, it's on page 21, and the header is Historical Background Part 3. If you're reading the historical background, that's great. I'm really quite interested in the history of these things, but you won't be tested on that. That's not part of this class. It's interesting, and especially if you're watching this video before the quarter starts. If you're just looking for something to do that will kind of get you engaged and ready for class to start, then you might enjoy that, or you might enjoy the technology use reading as well. But you're not going to be tested on either of those. So that'll do it for just now, and this is the last video in the review section, or the preview section of the course, the last stuff in Unit 0. So at this point, I will see you once the quarter actually starts. I'm not going to try to prove Abel's theorem. The proof is in your textbook if you're interested. I really just want the result from it because it's really quite handy. The nice thing about Abel's theorem is that it allows us to find the Wronskian for any two solutions of a second order linear homogeneous differential equation, even if we don't know what the solutions are. And that's pretty powerful. We're starting with the same conditions. If we have two solutions to a differential equation that looks like this, P and Q have to be continuous on some open interval I. If those conditions are met, then the Wronskian can be computed by taking C times e to the power of negative the integral of the function P of t dt. That's pretty powerful. So really, all I need is this function right here. For example, if you have the differential equation y double prime plus 3 over 2t y prime minus 1 over 2t squared y equals 0, then the Wronskian is simply c times e to the power of negative the integral of 3 over 2t dt, which is c e to the power of, this is pull the 3 halves out, and then I'm going to be integrating 1 over t. Well, that's the natural log of t, plus c. I should probably call that something else, right? We already have a c in this problem. Let's call it plus k. Now, it turns out we don't actually need that, because what we're trying to establish here is whether or not this thing is 0, right? So if I have a plus k, if k is 0, then I'm left with just this piece, right? That's my Wronskian. If k is non-zero, then I'm just adding to the exponent on the e. So I'm adding a multiple. Let me write it out. I'm going to have c e to the negative 3 halves, the natural log of t, times e to the k. Well, that is a non-zero constant. Even if k is 0, that's a non-zero constant. So I can erase that part. I really don't need it. And I don't need the plus k here either. And that simplifies things to no end. What is e? Let's just do a little algebra, just in case you're rusty. I'm going to use that power property of exponents to rewrite this as, the power property of logarithms to rewrite this as the natural log of t to the power of negative 3 halves. And that is c times e to the natural log of something is just the something. So that's going to give me t to the negative 3 halves. Now, if either c or t is 0, we're going to have a problem here, right? But the value of c will come from your initial conditions. So if C is 0, the Wronskian 0, and so you're not going to be able to find the values of C1 and C2 anyway, or not necessarily. It's not going to be obvious. It's not going to be guaranteed. If T is 0, then there's a place where the Wronskian will be 0, but everywhere else it will be non-zero. So T cannot be in our open interval I, but any other number will work. In fact, any other number, our interval can contain any other number. It just can't contain 0. In fact, in this case, T can't be 0 because this is equivalent to saying C over T to the 3 halves. So T can't be 0 because the whole thing would be undefined there. This is just an example, and it's just kind of a wrapping up of this section. It's been rather a long video. I apologize. But that's kind of the last really sort of piece that you need in order to be able to work through the exercises for this section. And in the next section, we're going to be talking about complex roots of the characteristic equation. So we're going to go back to solving equations like this one, where P and Q are just constant coefficients, but where when you solve the characteristic equation, that quadratic equation that comes out of assuming the solutions take the form e to the RT, the solutions to that characteristic equation are complex numbers rather than real numbers. What happens then? We haven't addressed that yet. So we're going to address that in the next section. For now, we're done with this one.